limits and continuity. Let's start off by talking about limits. So look at this theorem down below here. It says let fxy and gxy be defined for all xy not equal to ab in a neighborhood around ab, and assume the neighborhood is contained completely inside of the domain of f. Assume that L and M are real numbers such that the limit of f of xy as it approaches ab of f of xy equals L, and the limit of g of xy as xy approaches ab equals m. And let c be a constant. Then each of the following statements hold. So there's a lot of little rules here, but let's talk about what that means first for us. So off to the right here, I put a surface here. Now let's assume that it just has a hole in the middle there. And that middle I'm going to call AB. So I'm going to label it AB. And what it's saying here is it says, hey, there's a neighborhood around AB. So it's like I have this yard around it in a sense, and that's my neighborhood. And now assume the neighborhood is contained completely inside of the domain of f. So that domain is inside the f. Because if you think about this, that's giving me z values. So it's all in the domain. And then it says here that assume L and M are real numbers such that the limit as xy approaches ab of f of xy equals L. So that means it exists. So the limit has to exist for f and for g. And that's really what that's saying there. So that would be something like this. So let's say this value for z is 2. Let's say z equals 2. Now the way that this is different from 2 dimensions is I only had to look at the left and the right. And then if I was able to do that and said, hey, they gave me the same y value, then I could say, hey, the limit exists, and it's this number. So when I look at this 3-dimensional surface here, I have many different paths I can pick. I could pick a straight line going straight through it and check both those sides. And I could do it along the x-axis or the y-axis, or I could do it all kinds of ways. So those would just be lines. Another thing I could do is I could create parabolas that go through that point. Okay, and that's another thing I could do. I could create sine curves that go through the point. So there, I could do spiral. Spiral would be cool. So the thing is, when I have this idea of limit here, I have to consider every possible path in order to do some of these limits. So that's the more interesting thing about this. And we're going to get into techniques for that too. But this raises the complexity just because I have infinitely many paths, not just linear paths, but all kinds of paths. And it's not enough to just check one path to say that it's continuous. And that's the strange thing too. Or not continuous, I mean that the limit exists. So that's what we're going to get into more in this section now. Let's get hung up with all those different possibilities here. So for this limit of f of xy as xy approaches ab equaling L, that's saying, hey, no matter whatever path I take here, that the limit's going to exist. And that's really what it's saying there. And that's going to happen for f and for g. And then it says, now all of these statements hold. So now we've always had the limit rules. And I'm going to flip it to the next page because they're a little bigger on the next page. Hopefully you can see them a little better. So for this one it says, the constant law. That means the limit of a constant equals the constant. And then I have an identity law, which tells me the limit of xy as it approaches ab of x equals a. So in essence, I'm just plugging in the a for x. And the sum law, that if both of those limits exist on their own, that means they both go to some finite z value, then I can say I could break them apart and do the limits individually. And I can just say their sum is going to be the limit. And the difference law, subtraction, the same way. A constant multiple law. So I can take a constant and pull the constant out, take the limit, and then multiply it times the limit of fxy. I can do a product law. Now, this is the one that most of us never really pay attention to. But if each of those limits exist on their own, and the first one gives me an L, the second one gives me an M, that means I could take the limits individually and then times them together, and that limit will be good. The quotient law, I can divide. Now, again, keep in mind here the two conditions, well, the condition that needs to be true here, really two conditions because each one stands on its own, but the limits have to exist, and they have to go to some finite number, some finite z value. Okay, and then we have down below the quotient, we got the power law. So I can actually go inside of that and take the limit of the inside. And then after I'm done finding that limit, I can take it to the n power. All right, so they have a root law too, the same thing. I could take the limit of the inside, and then I can take the nth root of whatever I get to. So that's what's nice about all these. I can use these limit laws once I get it down. Once I understand those initial conditions hold. So that's it for this video. Now remember this, if one of those limits is infinity, but the other one's good, it's not good enough. They both have to go to some finite z value individually before I can use any of these statements.